So last time I discussed about localization techniques. So essentially localization means that you have some variety, and this variety is coming with an action of a torus, and you have a moduli space of, for instance, sheaves, curves, whatever on this variety, and you do count the invariance of this moduli space by looking at the torus fixed locus of the moduli space. And then this integral that we had, essentially, where is it? This is the integral. So essentially, for instance, here's the example where the moduli space of ideal sheaves, this one, I chi x beta, it had virtual dimension 0. So dt invariant is integral of 1 against the virtual cycle. But then if you look at instead of the whole moduli space as the torus fixed locus of it, this is that. And then you divide by the equivariant Euler class of the virtual normal bundle. And the virtual normal bundle was basically, we call it virtual normal bundle because it's just not a bundle. It's a complex, and it has higher cohomologies. And we are looking at the part of this complex which is moving by the action of the torus. So we write those moving parts in terms of the parameter t. T is the character of the action of the torus, equivariant character. And then essentially we get some invariant in terms of t. Now, if our torus is C star 3, of course, there's three characters, T1, T2, T3, and we get some function in terms of T1, T2, T3. All right, and then we discussed that sometimes this would be a particular torus, so the one that fixes the Calabi-Yau form or something like that, in which case T1 plus T2 plus T3 is 0. And if you include that in the calculation, you can kind of simplify the formula that you get, and we did that too. Okay, so this is that calculation here, and we simplified here to the McMahon function. Okay, so working over toric varieties is nice because identifying sheaves which are equivariant or invariant under this action of a torus essentially gives us some combinatorial picture of how to count them. So what if the variety does not have any torus action? If the variety X does not have a torus action, one can degenerate X into a toric variety and do the calculations there. So that's essentially what we want to do. We want to degenerate our variety into a toric variety, do the calculation on the toric variety, but then we want to reverse engineer this thing because we want to see how these invariants change, or if they are not going to change, why do they not change throughout this degeneration. So the goal is to recover the original varieties invariance from the invariance of the degeneration of this variety into the toric spaces. Before doing that, I need to tell you a little bit about degeneration itself. So let's talk about degeneration of sheaf moduli spaces. And relative DT theory. So this is some theory which is mainly, actually completely developed by Jun Lee and his former student, Baosen Wu. Really beautiful work, very interesting work. And so I give you some, to my capabilities, some exposition of what they actually did, okay? So let me tell you the meaning of these things. So degeneration, what is the relative doing in here, and so on. So let us start a story. I tell you the story, and hopefully along the story, the meaning of the word degeneration and the meaning of the word relative becomes clear to you, and the relationships, okay? So let's start the story. Here is the story. Given a smooth projective threefold, I want to work on threefold, X, and a smooth divisor, D, which is a subscheme of X, of subvariety of X. We are interested in subschemes of X, right? Which intersect D, transversely. Okay. Okay, so let's say I have X. This is my X. This is a subscheme of X. Let's call it Z. Yes. It could be, let's say, a curve, for instance. Okay. And then, obviously, O of X goes to O of this subscheme Z, and then it has an ideal sheaf of Z inside X that sits as a kernel of this map, surjective map, right? Now, first of all, I need to tell you what is the transverse intersection. Of course, transverse intersection pictorially means transverse intersection, but in terms of sheaves, it means the following. It means that transverse intersection means that the map, I of Z in X, ideal of Z in X, times the structure sheaf of this divisor to the structure sheaf itself is injected. Okay, so what does this really mean? Look at this exact sequence. So you have O of X, yes, and then you have O of Z, and then you have ideal of Z inside X, sitting inside here. If you tensor this thing by a structure sheaf of this divisor, then here you will get O of Z intersected with D, which is the normal tensor product of Z and D. And then this is just O of D, because this is the same exactly as O of X tensor with O of D, and that's just restriction of trivial bundle to the divisor, that's O of D. There you have O I of Z in X times O of D, which is the thing that we want. And then the next term is Tor1 as an OX modules of this multiplication of these two things, tensor product of these two things, which is OZ comma OD. Oops, okay, it's a bit bad, right? So let me write it. Tor1 as OX modules OZ OD. You see, if Z and D are non-transverse, if Z is not transverse to D, then this Tor OZOD will be non-zero, which then means that the map OIZ tensor O of D to O of D, you see this map over here? This is not injective. Okay, so this is translation between geometry and algebra. For instance, you could have some X which has a divisor inside it. So for instance, you could have some x, I can draw a cube for x, and I can draw a surface inside x, that's your divisor. Yes, and then I can draw a curve. This curve could meet this thing transversely and come and hit it, then go down and then hit it again, and then go. If it is like that, then in this case, ideal sheaf of Z and X tensor OD injects inside OD. It means that this term for it, this thing, will be actually equal to 0. But it's not always the case. It might be that this subscheme Z, this curve, for instance, and the surface are meeting non-transversely inside X. So for instance, you could have X like that, a threefold, and you could have some divisor in it. And you could have a curve that comes in some places, but then lies inside this surface itself completely and then gets out, for instance, at some point. So there is a locus of the curve, which is just falling inside that divisor, in which case, for this situation, there is for sure TOR1, OX, OD, OZ, which actually injects inside IZ of X times OD, and that goes to OD, and that goes to O of Z intersected with D. And this is Z intersected with D. So, you know, this thing is not going to be 0, and this is the algebraic meaning of transversality. Okay, so first of all, this is something we are interested in, that we are interested in finding situations where the subscheme is transversal. Okay, so if TOR1 OX OZ OD is equal to 0, that is algebraic transversality. Okay, so that's algebraic transversality. And then we are interested in the moduli space of ideal sheaves of Z inside X, which are algebraically transverse to D inside X. The divisor is the open locus, of all ideal sheaves inside OX, the subsheaves of OX, such that TOR vanishes for them. This is an open condition, ZD. This is an open condition. So if you look at all moduli space of ideal sheaves with certain Chern character and some curve class beta, then there is an open locus inside here, which is the moduli space of those sheaves with this transversality condition relative to D. So this is actually called relative moduli space. Okay, so you need to actually call it something. So you can actually call it so you can call it I chi x beta with relative condition to D, meaning with transversality relative to D. So this is that thing. This is that open locus inside here relative to D. Okay, it's an open space. All right, and you might ask, why is it at all? Why interested? Question. Why study this moduli space? That's the question you have. Okay, so let me remind you, or let me tell you what happened in the realm of Gromov-Witten theory and curve counting. So, reminder from Gromov-Witten theory. Okay, so we would like to calculate, you have a variety X and you're trying to calculate Riemann surfaces with certain pinched point here and there, curves basically inside X that are passing through some number of mark points. And the mark points are connected to some other cycles. You know, we did this thing before, so we don't care. Okay, this is the space that you're interested in. And this one is the curve Z, and the class of the curve is equal to beta inside homology theory of X. Okay, so you would like to calculate this thing. Then let's say X doesn't have any torus action, so localization is not possible. So one thing that you can do is you can degenerate X into a toric variety and then use degeneration on the level of the toric variety. So degenerate. And what does that mean? So you can degenerate X into a normal crossing variety. So this is X, and it meets, it becomes broken into a piece, and that second piece is another threefold that meets. So this is actually X. This is your original X. This I can call Y1. This I can call Y2. And then in the middle here, there is this divisor, which is the locus where the two pieces are connected to each other. Okay, so you might still say, what is this thing? Let's say X is given by set of this polynomial. So some polynomial, let's say some polynomial F of degree 5 polynomial, F5, in 5 variables, x0 to x4 inside P4 equal to 0. Quintic threefold is an example. Quintic threefold is an example. It is x0 to the 5th plus x1 to the 5th all the way to x4 to the 5th equal to 0. x0, x1 all the way to x4 are homogeneous coordinates of P4. You have a hypersurface inside P4. That's a 3 complex dimensional space. It's given by Fermat-Quintic equation. It just turns out that it's a Calabi-Yau, and that's the quintic threefold that we have. Now, I can put this into a family degenerating into the picture I just drew. So how do I do that? So construct a family. Construct a degeneration family. So what does that mean? It means the following. So you take some variable t, induce some variable t times f5 minus f1 times, for instance, to f4. Set it equal to 0. Okay. This is homogeneous of degree 5. This is homogeneous of degree 1. This is homogeneous of degree 4. Okay. So as a whole, f1 times f4 is homogeneous polynomial of degree 5 also. So the result is still some kind of a quintic. However, what this quintic looks like depends on the variable t. If t is not equal to 0, we get some smooth quintic inside P4, which is not necessarily one of these guys, but maybe it's isomorphic copy of it because it's just as smooth. But if t becomes equal to 0, then the equation becomes f1 times f4 becoming equal to 0, and the 0 locus of f1 times f4 equal to 0 is the 0 locus of f1 union 0 locus of f4. And that's what I'm going to call x1, or I called it y1, and that is basically y2. Y2 is the quartic, because it's 0 locus of the polynomial degree 4, quartic threefold. And this is just a hyperplane threefold inside P4. So this is just a copy of P3, you see. So in fact, this is our P3, and this is our quartic. And this line is the affine line. This exactly happens on t equal to 0, and this is happening on t not equal to 0. What is the business of doing all of that? Why do we play this game? Because as you can already see, one of these pieces already, this piece right here, is isomorphic to P3, you see? And P3 has an action of C star cubed on it. So via degeneration, you can take a variety and you degenerate it into pieces which are toric projective. Of course, X4 is not toric. It's projective, it's compact, it sits inside the P4, so it's a projective variety. It's not toric though, but that's fine. Later, you can take Y2 and degenerate it into another P3 and a cubic. And then you can take the cubic, degenerate it into P3 and a quadric. And you can take the quadric and degenerate it into two P3s. You see, at the end of this multifold degeneration process, you have ended up with absolutely completely toric varieties. Okay, so degeneration helps you to reduce your problem into some spaces where you can calculate things further. What happens to the curve in these spaces? The idea is the following. Junli was saying that if I'm supposed to count over the generic fiber of this family over A1, curves that I have drawn in here, then I hope that I can degenerate the variety, result of which is degeneration of the curve in the variety too. So maybe the curve becomes something that meets this divisor here, and then it breaks into some other piece that lives in here. Yes, so the curve also breaks into pieces C1 and C2. So we would like C1 and C2 to be result of degeneration of the curve, or Z1 and Z2, sorry, Z1 and Z2, Z1 and Z2, or C1 and Z2. So we would like C1, Z1, and Z2 to be result of this degeneration. We would like Z1 and Z2 to be results of degeneration of Z. Because Z lived in the original variety and now the original variety is broken into pieces, you would like to think of Z as a system of a pair of curves, Z1, Z2, such that they glue nicely on this divisor, meaning that their profile, intersection profile with the divisor needs to match. So the profile, intersection profile, that is, i.e., intersection profile of Z1 and Z2 on D need to match. Furthermore, because we would like to think of intersection as some points with multiplicity, as you can see from the picture. If any of the curves Z1 and Z2 fall, or a piece of them falls inside that divisor, we don't like that. Furthermore, we would like Z1 and Z2 to be transverse to D. So hence we would like to count Z in X by counting Z1 in Y1 and Z2 in Y2 such that Z1 and Z2 meet D transversely with compatible intersection profiles. Okay, that's why we are interested in transversality of a subscheme with respect to a divisor. This divisor D, this surface D, as you can see from the picture, is a divisor inside Y1. It's also a divisor inside Y2. I'm counting curves like Z1 inside Y1, and I'm counting curves like Z2 inside Y2. But I'm not interested in all possible curves. I'm interested in the ones that are transverse to the divisor in the middle. Okay, that's what we are trying to do. Okay, any questions so far?
I think I have one.
Go ahead.
So
Yeah.
how could D be a divisor in both the spaces, the quartic and B3 at the same time?
Well, yes, it's possible, right? I mean, inside this Y2, D is a hypersurface, hyperplane, yes. And inside P3, it's a surface of degree 4. Literally, look at the picture, right? There are two threefolds, and they're glued along this side of them. The side is boundary, and the boundary is in common between the two. So D is a divisor inside Y1. It sits inside Y1, and it sits inside Y2. For both of them, it's a divisor. What is the issue?
No, okay. I mixed the degree.
Yeah. So D is a quartic inside P3. So D, in our example, D is a quartic surface inside P3. Okay, and that is also a Calabi-Yau surface, so it is a K3 surface. As a divisor in Y2, which itself is quartic, D inside there is a hyperplane, The point is that D needs to have degree 4 as a surface. Inside Y2, it's a hyperplane, so naturally inside it's like if you derive it as its equation as variables of P3 will be degree 4. So this ambient space itself is degree 4. So if you intersect it with the hyperplane, the result of intersection is a degree 4 thing. So it's the K3. This space P3 is itself just P3 hyperplane. So if you intersect it with the quartic, you also get the same thing, D. Yeah?
Okay, thanks.
Okay, sure. So, all right, so that's what it is. And you're trying to count these curves with this profile along that divisor in the middle. Right? And so this is what you're interested in. Now you might say that what if Z1 or Z2 or both are not transverse to D. Then counting them, the ones which are result of this degeneration will be very difficult. Then there is something we would like to do, which is make them transverse, okay? So in some sense, if we are interested in, so in some sense, we have the moduli space of curves inside X, and we are trying to degenerate it to the moduli space of curves Z1 inside Y1 and Z2 inside Y2 relative to D and relative to D, which match with each other. The point is, though, that these two spaces both are open because, as you saw, transversality is an open condition. So these are both sitting as an open loci inside moduli spaces, their corresponding moduli spaces. So this is an open locus inside moduli space of all curves inside Y1. And this is also open locus inside moduli space of all curves inside Y2. And counting over open, counting is always an integral. And if this locus, if this guy is open, and if this guy is also open, how can you define an integral on it? So you need to somehow find the compactification. We need to compactify mz1 inside y1 relative to d, and mz2 inside y2 also relative to d. Compactification means you need to find a way of, compactification means if you have either of the yi's, so if you have yi, I from one or two, doesn't matter, and you have this d, and you have one of the curves, either side, that kind of lies somehow inside d somehow, zi, if you have that, you need to replace this with something equivalent, which is transverse to D, or satisfies the transversality condition to D. Otherwise, this locus where they are transverse is always open. Not all of them are transverse. In the limit, some of them fall into the divisor. You need to do something about it. How do we do that? Okay. So let me tell you. We can use, in order to, okay, so let me write everything we said. We need to come up with a compactification of the open locus of relative ideal sheaves I, Z inside X, or here we are trying to compactify Zi inside Yi, Z1 inside Y1, and Z2 inside Y2, yes. Ideal sheaves, in order to define integrations and invariants on their moduli spaces, on their corresponding moduli space. All right, so one of the remedies of it is the following. So on the corresponding moduli spaces. So the remedy is to allow to blow up, basically. Let me write it like this, to blow up. So I'm gonna first write it, blow up, okay, blow up this family along the normal cone to D. Okay, what does that mean? And where is it coming from? And what good is it for? So this is, by the way, due to William Fulton, and McPherson construction. Okay, so this is that construction. So let me show you what is degeneration to the normal cone, or blow up to the normal cone, degeneration to the normal cone is really. So this is what it is. So take this variety, take this family. On the generic fiber of it, I have X. For now, don't worry at all about the curves inside X. I have X for t not equal to 0, or some isomorphic copy of X. And for t equal to 0, X breaks into pieces, as you saw, and it becomes two pieces attached along D. Yes, so it becomes something like this. And the middle piece there is D. Okay. Call this base of this family is A1. On the generic fibers, I have always isomorphic copies of X all the time, isomorphic copies of X. Only on the special fiber, I have Y1 union Y2 meeting along D. Okay. Call the total space of this family, total space of it, call it something, call it curly X, total space. So curly X is obviously a fourfold. Its fibers are threefolds, and the base of it is A1, affine line. It's a threefold fibration over the affine line. Yes. So what you can do is actually the following. You can take this family. Yes. So you can actually take the whole family, blow it up along. So this is X times A1, right? You can take X times A1, the whole family, blow it up along D times 0 point inside A1. I guess you know that if I have a family, if I look at the total space of this family like this, any scheme inside this family you can give me, then I can blow up the whole family along that scheme. What that does is that it replaces every point of that scheme with a P1. Okay. So what is the scheme I'm picking inside this family? It's a particular subscheme of the family. It is exactly, the subscheme is D, which is in the fiber, lives in the fiber, D is in the fiber, right? Because D sits inside the threefold that lives in the fiber, and over the point T equal to 0 in A1. What happens to this? What does this look like? Let's call this a new thing. Let's call it X prime, this new family, or curly X prime. If I define curly X prime, I would have drawn the A1, okay? On the T not equal to 0, nothing happens to this family because this blow-up cares exactly where you do the modification to the family. It says don't touch the fibers as long as T's become equal to 0, okay? As long as T is not equal to 0, this is T equal to 0, right? Don't touch the fiber. Okay, I'm not touching the fiber. So I still get X. And then it says, touch the fiber exactly where T becomes equal to 0. Here is T becomes equal to 0. Touch the fiber in the sense that blow up that fiber along D. What that means is that you have this part. This is your Y1. This was your D. You blow up D. Every point of D gets replaced by a P1. Every point of it. So you will get a cylinder. This cylinder has two caps. Both of them are isomorphic with D because P1 has two points, 0 point and infinity point. So this cylinder has the 0 section and the infinity section. If I blow up every point of D only, that means that every point of it is replaced by P1. So I will get a cylinder with 0 and infinity sections. And then what happens to Y2? Y2 is still attached to it. So Y2 gets attached to the infinity section right here. That's where Y2 lives. Okay. What is good in doing this? What is good in doing this is the following. If you started from the curve Z, and the curve Z was here, and then some part of the curve was coming and falling inside this D, this is your curve Z1, for instance. When D stretches out accordionically, like an accordion, and becomes the cylinder, this curve has to also stretch inside the cylinder. So if it was falling inside the divisor, now it's being stretched, pulled, and it cannot be falling inside the divisor anymore because it will be sent somewhere to the fibers of the cylinder, but the end of it might still fall inside the divisor. So on one side of the cylinder, for sure, this curve becomes transverse. Okay, is this clear, Mohammed?
Yes, it is.
Excellent. So as we can see is that, so it might be that after blowing up x times a1 along d in x and t equal to 0 in a1, curve z1 is transverse to one of the copies of d inside the cylinder, but not transverse to the other copy. Say in this case, the infinity section. If that happens, you blow it up again. If this is the case, blow up the new family x prime along d times 0 again. Okay, if you did that, blow up of x tilde times d times 0 would be a new family. Again, nothing has changed over the generic fibers. Still, I have that x. Still, I have the curve inside x. But then, what happens over here is that now I have y1 and the d. I have one of the cylinders, and then I have another cylinder that I will see, and then I will have y2. So this is y1. This is a copy of D. This is a copy of D. This is a copy of D. This is y2. This is the 0 section of this cylinder. This is in the infinity section of this cylinder. As the second cylinder, this is also the 0 section of the next cylinder, and this is the infinity section of the next cylinder. What happens to the curve is that now the curve was transverse to the first one. It became transverse to the second one, and it might be transverse or not in the third one. As long as the curve is not transverse to this divisor, you need to blow up and blow up and blow up. And Jun Lee showed that after finitely many blow-ups, the ideal sheaf I of Zi inside Yi becomes transverse to D1 in Y1 and D2 in Y2. So the whole thing is that you replace this picture where Y1 and Y2 are connected to each other exactly along D. You kind of take it in the middle, and like an accordion, you expand it, open it. This accordion opens up from right the middle, and then the curve eventually becomes transverse to both sides of this accordion, which are the divisors in Y1 and your Y2 that you're interested in. Okay, so like that. Okay, so if you replace the boundary of that open locus with this picture, that's exactly the compactification. Basically, the compactification will be, so if you have moduli space of Zi inside Yi with the relative condition, so okay, so this is the big moduli space of Zi inside Yi. Inside it, there is this open locus, because the eyes are not necessarily transverse to D, doesn't satisfy the compactification, but then you put a boundary on it. And this boundary corresponds to pictures which look like Y1, an accordionic expansion of it, essentially Y2 with curve Z1 expanding all the way Z1 and Z2. So this is what you pick as the point on the boundary of compactification. Okay. All right. Is this clear?
Perfectly clear.
Perfect. Okay. Okay. All right. So this is what they do, and okay. So now, what is the procedure then? So this provides compactifications M of Zi inside Yi with the relative condition to D with the bar on it. Okay, so if I have original moduli space Z inside X, I'm degenerating it first to M of Z1 inside Y1 with relative condition along D, and M of Z2 inside Y2 relative condition along D. This is open inside M of Z1 inside Y1. This is M of Z2 inside Y2, also open. And in the middle, I close them up with this choice of compactification by adding these accordionic expansions, or they call them expanded degeneration. So this is called expanded degeneration. Okay. All right, so how do you define the invariant? Now it is easy. So M of Z in X has degenerated to M of Z1 in Y1 over D, compactified, times M of Z2 in Y2 with relative conditions on D, also compacted. Now, if you look at the pictures, there are maps, restriction maps from this restriction map R1, R2, 2. So if you look at one of these pictures now, so in here, I'm looking at pictures where on one side I have Y1 and there's some cylinder, okay, but on the other side I have eventually Y2. So this is D and this is D, and this is Y2. But then I have the curve meeting transversely, and the curve on this side also meeting transversely. Yes. So I need to match the profile of these things. And the reason I can do this, because in algebraic geometry, everything is up to isomorphism. Because the two Ds are isomorphic to each other, I can think of them as one. So all I want to say is that restriction of Z1 want restriction of Z1 on D to be the same as restriction of Z2 to D onto D. Yes, restriction of them is these points, right? So you want to match the points with each other. So all you're trying to do is actually to, so if I look at these moduli spaces and I restrict to D, I get that on D, the picture I'm looking at is a configuration of points. Now that I know my curves are transverse, I'm looking at configuration of points. So via restriction R1 times R2, so let me write it like this. This moduli space of curves in Y1 restricts in D to moduli space of points in D, and that's the Hilbert scheme of some number of points, n times points inside D. And same thing, some Hilbert scheme of n2 some number of points inside D. Okay, so we obviously we want n1 and n2 to be the same and to be actually in the same location. Okay, so what does that mean? I want to look at the locus inside the product of these two Hilbert schemes where n1 points and n2 points are equal. So that's exactly the diagonal, right? So the diagonal actually sits inside here. So this is the diagonal. So diagonal is the locus where n1 points and n2 points are the same. N1 and n2 are the same. Okay, that's good. So let's call this a diagonal embedding something I of delta. So eventually, I would like to say that I'm interested in terms of the virtual fundamental class, I'm interested in I of delta upper Schrick. This is the Kisin pullback of the virtual cycle of mz1 inside y1 with relative condition along D times mz2 sitting inside y2 with relative condition along D. And what is this Kisin pullback does? It gives you the virtual cycle of the locus where n1 and n2 are equal. That's exactly the diagonal, virtual cycle of this diagonal. So diagonal sits inside here. There is something that sits inside here, and that's the virtual cycle we are interested in. And I am just looking at this fiber diagram. Okay, that would be this thing, the virtual cycle. I'm going to call it virtual cycle of the moduli space over the t equal to 0. Why? Because this is the virtual cycle of a locus of curves in y1 and curves in y2 such that after restriction to the divisor d, n1 points you get after restriction of z1 exactly match with n2 points you get after restriction of z2 to d. This is why this is the virtual cycle of the special fiber of the family. Yes. Okay, so that's what we are trying to do. So in some sense, we have degenerated the virtual cycle of the moduli space of curves inside X to this thing, I delta upper Schrick of M1, M of Z1 in Y1 with D compactified virtual times M of Z2 inside Y2 with D compactified virtual. Okay, that's what we are doing. But then you might say, is this true? I mean, is there only one choice of such compactification? No, because the curve class beta now still is free. So this curve inside here can have curve class beta 1, and this can have curve class beta 2. So there are so many ways of breaking beta into beta 1 and beta 2. So basically the statement is, the virtual cycle is the sum over all possible ways of breaking the curve of these things. So M of Z1 inside Y1 relative to D virtual, where class of Z1 is equal to beta 1 times the other one, M of Z2 inside Y2 relative to D virtual, where class of Z2 is equal to beta 2. All possible ways need to add, and all possible ways of breaking the curve into two pieces will contribute to the original virtual cycle. Because you have this thing, obviously, then integral against this virtual cycle is equal to sum of the integrals that you will see against the two of them. So integral of this virtual cycle times integral of the other virtual cycle. Okay, that's basically the story of degeneration. And okay, because of this, you can actually see that in case of Gromov-Witten invariance, in case of Gromov-Witten theory, the partition function of Gromov-Witten invariance for X, some number of mark points, curve class beta becomes the product of the two partition functions of Y1 with some number of points PR beta 1 times Z2 Y2, some number of points PR plus 1 PR Pn beta 2. Beta equal to beta 1 plus beta 2. Okay, this is the level of the partition function. So this is in the level of partition functions. Okay, so that's what this becomes. And okay, is there any question? Are you there? Let me actually go back. Let me first of all, I see how many people are here. Any questions, guys? No. Okay. All right. So it's clear, or is it clear or not? Do you have any comments? Okay. If not, so this is basically the degeneration. Okay. So let me tell you some facts about this degeneration technology. Okay. Let's see. One fact is that, fact one, in finding the choice for boundary of relative moduli spaces, M of Zi inside Yi with relative condition long D, we need to make sure that stretching the curves along the cylinders, these cylinders, by the way, are called bubbles, is independent of parameterization of the bubble. Parameterization of the bubble. What does this mean? Well, when you have your X with the curve in it and you degenerate it into normal crossing variety and then stretch it inside the cylinder maybe some number of times. Let's say in this picture I have bubbles. So this is bubble 1. This is bubble 2. Okay. And as you look at your curve, it's kind of stretched out like this and then becomes like that. You need to make sure that, so these bubbles are essentially P1 bundles, okay? So this is the fibers are P1. So every fiber of this thing is P1 and every fiber of this thing is also P1. Each fiber of P1 is acted on by the action of C star, and here same. So C star is acting on these things. And the parameterization of this, so this is basically a P1 bundle on this divisor D. It's the projectivization of O of D plus normal bundle of D inside Y1, for instance. That's what it is, okay? This is what that P1 bundle is. And P1 bundle, its fibers are being acted by C star. So you need to make sure that location where the curve is being sent to along the fiber does not depend on this action of C star. So when you look at this, there is a scheme that parameterizes all pictures like this. So there is a parameterizing scheme of parameterizing all of these possible pictures where the curve is stretched along this with the C star action and this with the C star action. Of course, there is a scheme that parameterizes pictures like this, but you need to mod out by the actions of C star. So you mod out by the action of C star times C star. So this C star action only moves things inside this cylinder and doesn't act on any of the other cylinders. So that's how the action is defined. And the other one only acts on its own cylinder. If there are R bubbles, you will have eventually R many C stars that you need to mod out with. So essentially your moduli space, your suitable moduli space is the moduli space where it's a scheme parameterizing pictures stretched, accordionic stretching of the variety with the curves in it, modulo the action of C stars, so that your construction doesn't depend on that action, okay? Why is this important? Because if you don't work with, this becomes essential, this becomes essential and important, since if we do not work with ideal sheaves or curves, sorry, this is very, very annoying. Give me a second. Okay, if we do not work with ideal sheaves or curves themselves, after, for instance, let's say, say we work with general coherent sheaf moduli spaces, modding out by C star to the R might leave us with a non-separated ill-behaved moduli space over which no computation could be possible. Could be possible. So this technology so far, this technology works for ideal sheaves, what is called the stable PT pairs, which I didn't talk about, and curves. In order to extend it to all coherent sheaf moduli space degenerations, we need to use additional constructions and derive the algebraic geometry. Okay. All right. So this is actually one of the main issues that when you're working with curves and ideal sheaves of curves or ideal sheaves of anything, it works. But if you're working with other types of sheaves, it doesn't. Okay. So this is one of those issues. All right. Anyway, so after computing relative dt or relative Gromov-Witten invariants, we have also the relative version of Gromov-Witten Donaldson-Thomas correspondence. Okay, so which is this? It is minus I times U to the virtual dimension of the moduli space of stable map moduli space plus L of mu minus cardinality of mu. I will tell you what mu is, times Z prime of Gromov-Witten invariant X over D U and then R1 gamma 1 gamma R mu beta, okay, becomes minus Q to virtual dimension of the dt moduli space divided by 2 Z prime of dt X over D variable is Q gamma 1 gamma R mu curve class 8 after change of variable e to the IU equal to minus Q, and here virtual dimension is equal to minus canonical bundle of X times the curve class beta. Okay. All right. So I need to tell you what mu, gamma 1, and gamma 2, and so on are. Okay. So I need to tell you those things. So let me at least tell you what that is. Okay, so the picture is as follows. So if I have X, and I have degenerated X into a normal crossing along a divisor, like that, roughly speaking, I don't need to, for now, accordionically expand it. You know that there is an expansion involved. This is D, and I have curves Z with curve class beta in here, and I have curves Z1 with curve class beta 1 here, and Z2 with curve class beta 2 in here. And this mu that we are involving inside here is the profile of Z1 and Z2. So this is basically mu1 and mu2, and we would like mu1 to be exactly equal to mu2 equal to the profile of it. This profile is telling us number of points of intersection, number of points of transverse intersection, with multiplicity. Okay, so that's what it is. And then, okay, so I have these, these gamma 1 to gamma r, the cycle classes that, you just have some cycles inside this variety, Z1 to ZR, and you're trying to basically calculate some R-pointed integral. Okay, so this is what that is. Okay, so this is the relative version of the Gromov-Witten and Donaldson-Thomas correspondence. Okay. All right. Any questions? Good. Yeah. So the idea is really that you have the variety X, you have broken X into pieces. If you have curve inside X, you would like the curve to break into curve C, Z1 and Z2 with transverse intersection along D. That's an issue. You need to make the curve transverse. That is involving this bubbling phenomena. So on the very boundary where the curve actually falls inside the divisor, you accordion-ically expand these two things and make it so expanded degeneration to a point that the curve on all loci and all isomorphic copies of P becomes transverse to all of them. As you do that, you are trying to close up the boundary of this open locus. That's a moduli space itself. That's a locus, right? That moduli space needs to be well defined. Each one of the bubbles come with the C star action. So you need to take the scheme that parameterizes all such complicated pictures, mod out by the action of C stars. Because this curve should not care about how the C star is moving things around inside the bubbles. To mod out by those things, that's the choice of compactification. Turns out that Jun-Lee and Bowes-and-Wu's result is very important because, by the way, Gromov-Witten degeneration completely was figured out by Jun-Lee himself. And Donaldson-Thomas degeneration for ideal sheaves and PT stable pairs was figured out by Jun-Lee and his student, former student Bowes-and-Wu, who is now in Hong Kong. Himself is a senior professor. The proof is multifold. One of them is that after finitely many bubblings, this thing becomes completely transverse. That's one. Second part is that if I mod out by these C star actions, I get something well behaved. That's very important. When you work with ideal sheaves or PT stable pairs, they show that it's true. You can, after finitely many times, don't worry about transversality, and modding out by C star gives you still nice moduli space. For general coherent sheaves, this doesn't work. Okay. My collaborators and I have worked on this general coherent sheaf degeneration for a very, very long time. And we have come to the conclusion that you need to use technology of derived geometry to work out analog of this for general coherent sheaves. But for the purpose of enumerative geometry, especially relation between Donaldson-Thomas and Gromov-Witten invariants, what Lee and Wu created completely finishes the problem. And okay, so we did that. Then the last part of the summary of today's session is that, so what is the story? What is the message? Invariance of the original variety can be written as the product of invariance of the relative curves or relative sheaves on each one of y1, y2. Those are themselves invariants. Invariance of curves in y1 with a certain profile along the invariance of curves in y2 with certain profile along the. If I can calculate relative invariance, is there a relation between Gromov-Witten and dt? But the relative version of those things, yes, there is. And the last formula I put there is the correspondence. The relative version. On the Gromov-Witten side, I think relativity is just completely as it is. Relative curve means it intersects transversely to the divisor. On the dt side, relativity is the algebraic transversality condition, which means that I, ideal sheaf times O of D, injects inside O of D, means that Tor1 vanishes. So that's basically that. And so you get this correspondence, the relative version of this course. Okay. No questions?
Yeah, I have one. So you've given like the example of the quintic threefold, and you said that after the generation we end up with P3 and the quartic, and then we continue doing this until we have like torus action both. So if we do this an example like this, for example, and we keep doing this a couple of times, do we do this bubbling in between each of one of these, or are they already a bubble since they are P's themselves?
Yes, there's you see, the bubbling phenomenon is in the level of the moduli space. There are two things that are happening in parallel. It's like two workshops. One of them is depending on the other. First workshop is the very geometric workshop, the place where these curves live in. That's the variety. And you're trying to relate varieties of curve counting or shift counting in X, curve counting or shift counting inside something toric. In order to get to that point, you need to keep degenerating. In each level of degeneration, invariance of the generic fiber of degeneration becomes the product of relative invariance. So for instance, invariance of curves in X becomes relative curves in P3 times relative curves in quartic. Then relative curves, then you need to, okay, so that's that. Now, if you were counting curves in quartic becomes relative curves in cubic times relative curves in times P3 again. Yeah. Now there is a missing piece in here. What is the relevance between curves in quartic and relative curves in quartic? You see, what is on the right-hand side of the equation is always relative curves, and what is on the left-hand side of the equation is always absolute curves. Yeah. So absolute curves in quintic becomes relative curves in quartic, relative curves in P3, good. Absolute curves in quartic becomes relative curves in cubic and P3. In order to relate these two lines of equations, you need to find a relation between relative curves in quartic and absolute curves in quartic. And that's its own business, which I haven't yet told you. Eventually, this very, very involved system of degeneration of the variety and bubblings of phenomena on the level of moduli space in each one of the degenerations gets all related to each other. And that's a result of, if you really want to know, this recipe was given by Malik and Pandri-Pandey in my opinion, one of the most important papers a long time ago. And it was worked out with a lot of detail by Pandri-Pandey and Aaron Pixton in a series of papers. It's very involved because relating relative invariance to absolute invariance is also itself a certain technology on its own. Goal was for them to prove the Gromov-Witten and Donaldson-Thomas correspondence for quintic threefold. Yeah, and they proved it by degenerating dt moduli space and Gromov-Witten moduli space all to these toric pieces and identifying the relative invariance that way. Basically, so they did the problem for the Gromov-Witten case and for the dt case, and then found a system of identification of the two partition functions, which is very, very involved. I mean, one can do a thesis on the result, in my opinion.
Yeah. It's like
It's
each
a very,
problem
very
just bubbles
long,
into.
it's a long chain of, but I'm kind of, the goal behind these lectures is kind of expose you to what is out there. And the reason we are not going, sometimes we are going into some details, sometimes we are not going, is because I want you to just see it. But probably in the second course after this, Gromov-Witten 2 or something, we can go pick one of these papers. That will be like a seminar. We can go and really write everything on the blackboard and try to very rigorously
Okay.
see what they did, and then see if we can extend what they did. That takes a long time. Okay. All right. But I'm kind of telling you a very vague story because that's the purpose anyway, to kind of familiarize you with some of the current technology. All right. So let us end the discussion today. Next time, I will go to say a little bit more about these degenerations, and then we talk about torsion sheaf invariants.